Okay, incidentally, regarding the weather on Thursday, it's supposed to be basically like this. So because it's out in the high desert in Santa Clarita, it's probably gonna be in the upper 70s or something like that, so you know, dress appropriately for that. I don't know, sunscreen is probably a good idea. With respect to food and water, the park won't let you bring anything in, so you're gonna have to buy concessions. When it comes to concessions at this park, believe me, not all food is created equal. But make sure that you bring some money to use, of course, as well. Okay? All right, so let's go ahead now and get started with the remainder here of today. Let's go ahead and begin chapter 16, which is on specifically sound. So it's a continuation of waves, but we now focus in on a specific wave. So first of all, what exactly is a sound wave?
Is this our last chapter?
Not even close.
Oh. No, okay.
Okay, a sound wave is a longitudinal wave that propagates through a gas, such as the air, or a liquid, such as water. But it does so three-dimensionally along spherical wavefronts. So it's a longitudinal wave. It propagates through a gas or a liquid. And it does so three-dimensional. It's a three-dimensional geometry with spherical wavefronts. Now it has to be three-dimensional, of course, for the following reason. If you're in front of me, you can hear me. If you're behind me, you can hear me. If you're to my right, you can hear me. If you're to my left, you can hear me. If I was up on the ceiling, you could hear me. If I was down there, you can hear me. So obviously it's a three-dimensional propagation. It's a little bit difficult to picture, however, exactly what is happening with the air molecules or water molecules, because of course you can't see either. So a little bit of animation here acts as a visual aid for us. And I'm just going to take a look at the top animation here on the screen. Okay, so with the top animation, what we have here are just air molecules, for example. And then as I speak to you, by the way, I'm speaking to you with a short range of frequencies. If I was, however, to speak to you with one frequency, and I do this continuously, so I would just go, like so, then propagating through the air would be a simple periodic wave that looks like this in the animation. Now, as the wave propagates, if you kind of focus in on an individual air molecule, it's just oscillating back and forth, so it is a simple periodic wave. The portions of the wave where the air molecules are close together, we refer to that as a compression. And then mathematically, we think of that as a crest. Where the air molecules are far apart from each other, this is referred to as a rarefaction. That's the same root word, like in the term rarefied air. We think of that as a trough. So that's just very simply a simple periodic wave that is propagating through a gas, such as the air, or a liquid, such as water. Now what this animation doesn't show is it does not show the already present random motions of the molecules of a gas. For example, the air inside this room. Okay, the air inside this room, we'll say, is just at 70 degrees Fahrenheit. Basically what temperature is it's a measurement of average kinetic energy. So right now, all the gas, all the air molecules here in this room are moving around, they're colliding with each other, colliding with objects, etc., etc. That's not being shown here in the animation. So that already random motion is present. It's just when I speak to you, then through that propagation, we then see the longitudinal wave like so. So that's basically what's occurring. So then therefore, based upon that animation, you can now understand the following diagram, which you'll typically see in textbooks and whatnot. Kind of looks something like this. What I'm going to draw here is basically a full wavelength. So we start off with air molecules bunched together like so. And then further apart over here, and then bunched together here. And then, as I said a few minutes ago, where the air molecules are bunched together, we refer to that as a compression. The air molecules are compressed. here, and here. And then we think of that mathematically as corresponding to crests. And then here in between, where the molecules are far apart from each other, we refer to that as a rarefaction. Here's how you spell the word. So, and then mathematically we think of that as corresponding to a trough. So what I've drawn here is just one wavelength. We're going from crest to trough to crest, like so. So right here is the distance lambda, and then just in terms of the basic kinematics, once again, speed equals wavelength times frequency. Now that's just kind of like a close-up focus of the molecules themselves, but you would have to picture the three-dimensionality of the wave in the following way. Kind of like similar to drawing a two-dimensional situation for circular water waves. So let's say that right here is just a point source of sound. Assume that my voice is a point source just for simplicity, and instead of speaking with a range of frequencies, I just do this at one frequency continuously, like so. And then propagating outwards from there, then, you would have spherical wavefronts. You would have wave crests, for example, where you have these compression regions. Just draw that as a series here of concentric circles, however, like so. But keep in mind that this is a three-dimensional situation, not two-dimensional like water waves. So you have, once again here, just for clarity, three-dimensional spherical wavefronts. So what I drew up on the top board is obviously kind of like focusing in right here on this crest and focusing in right here on this crest. So this distance here from crest to crest is the wavelength, and then once again speed equals a wavelength times frequency. So overall, the three-dimensional geometry just looks like this. If we look at the details of the molecules themselves, they look like the top board. Okay, now a couple of the details associated with first the speed of sound and then the frequencies. First of all, the speed. Okay, applying F equals ma to a gas or to a liquid to derive the speed of sound is rather difficult to do. It involves some fluid mechanics, which is beyond the scope of this class. But basically, it essentially all just boils down to this. The speed of sound in air, for example, just depends upon the properties of the air. It depends upon its density, it depends upon air pressure, it depends upon temperature, and so on. So in other words, the properties associated with a gas. Now, those quantities are constantly changing by very minute amounts all the time. So this then means that the speed of sound is constantly changing. But it very nearly always is the same number when the conditions are basically the same. So if you're talking about just normal atmospheric pressure, like we are here at sea level, and then just at normal room temperature, roughly 70 degrees Fahrenheit, the speed of sound is very nearly a constant. It's about 343 meters per second. And once again, the number itself, if we were going to derive it, and it has to do with the density of the air, the temperature, pressure, and blah, blah, blah. Now, just to give you a little bit of comparison, how many of you have ever been in a swimming pool underneath the water's surface, and you listen to sounds from coming on the other side of the pool, for example, it kind of sounds a little funny, right? Well, one of the reasons why it does is because in the denser material, the liquid, the water, the speed of sound there is considerably greater than it is in air. It's almost 5 times as much. The speed of sound in water I don't remember the exact number off the top of my head, but it's in the neighborhood of like 1,400 meters per second, which is considerably faster than it is in air. Okay, getting back to the speed of sound in air, we're actually going to measure this value. Now, if I said to you, how do you measure the speed of sound, you would say, oh, boy, that's probably really hard to do. It turns out it's actually really easy to do. And it's easy to get an accurate result. We'll do that as a lab exercise late next week after we get past our magic mountain trip. Okay, now frequencies. Okay, frequency F, as it always is just waves per second, measured in hertz. Okay, this is a physical quantity, as we've been talking about it since chapter 5. However, when it comes to our physiology, we use the terms pitch and tone to describe the sound. The pitch corresponds directly to the physical quantity of frequency. In other words, a low-pitched sound, that corresponds to a low frequency. A high-pitched sound, that corresponds to a high frequency. And then the tone is sometimes used to refer to what the quality of the sound is, whether or not it sounds pleasing to your ear, for example. So we use the words or the terms pitch and tone. Physiological terms, pitch and tone correspond to frequency. Brian, I'm assuming it's an emergency? Okay, now the range of audible tones to the human ear, the frequency spectrum as it's sometimes called, is actually quite large. The range of audible sounds to a person. And frequency spectrum, as it's sometimes called, is quite large. We can hear sounds with a frequency as low as about 20 hertz, really low bass tones, for example. But then at the high end of the spectrum, we can hear frequencies of really high-pitched sounds of up to about 20,000 hertz. So there's a range here by a factor of 1,000 in terms of the frequency spectrum that is audible to human ears. Okay, I'm actually going to demonstrate this to you. I can demonstrate this range very easily. Let me make it as quiet here in the room as I possibly can. Okay, unfortunately, I can't do much about the electronic hum that you hear coming from the speakers. It has to do with the current and whatnot. There's nothing I can do about that. However, right here I've got a function generator. And the function generator here is capable of producing just pure frequencies, one single sine curve, and then I can adjust the frequency as I want. The output here, of course, is going to be coming out of the speaker. Okay, now, once this warms up, there we go. What you're hearing right now is a frequency of 400 hertz. This is 500 hertz, for example. This is 600 hertz. And now what I'm going to do is lower it. I'm going to lower it from 600 to 60 hertz. Wrong switch. There we go. Hear that really low-pitched hum? Notice it's softer sounding. I didn't change the volume, I just changed the frequency. The reason why it's kind of soft sounding is we're getting down towards the low end here of what you can actually hear. And now I'm going to ramp it all the way down to 20. It will get softer as we do, and the only reason that is because we're getting close to the low end portion of the frequency spectrum. So once again, this is 60 hertz, 50, 40, 30, and now down to past 20. And you probably can't hear it at all. Okay, I'm going to come back up. Like so. That right there is 80 hertz. Okay, I'm going to jump up to 800. And in just a few moments, I'll jump up to 8,000 and then move up from there. But before I do, let's see exactly how good everybody's hearing is. So what I'm going to have you do in a moment when I flip it to 8,000 hertz and then go up towards 20, is I'm going to have you keep your hand up until you can't hear the sound anymore. And when you can no longer hear it, then lower your hand. I'll do this as well. I'm going to tell you right now, I'm going to be the first person that lowers their hand. The reason why is because as you age, your physiology changes, your ability to hear high frequency sounds begins to go down. Your ability to hear high frequency sounds also goes down as you damage your hearing, which I have done repeatedly over the years. These ears have been subjected to literally thousands of concerts in the last 30 years. I go to concerts all the time. I'll tell you how you want to protect your hearing a little bit later on today. But suffice it to say, I'm going to be the first person that puts their hand down. Okay? So once again, this right here is 800.
Quick question.
Yeah.
Is this gonna blast our ears when?
No, because I'm keeping the volume low. It may be so kind of annoying, but I'm not going to blast your ears because the volume's low. Okay?
Yeah,
All right, so everybody here can hear this. Okay? This is 8,000 hertz. Okay, let's go up from there. 9,000. 10, 11, 12, 13. I can't hear that. It's 14,000 hertz. I can't hear it. 15, 16, 17, 18, 19, and that's past 20,000 hertz. Now, right now, there is still sound coming from that speaker. You can't hear it, however, because we're above the range of audible hearing. However, if I was to turn the volume way up, then even though you can't hear it, I could actually still damage your hearing because the energy is still coming from the speaker and striking your ears. Now, don't worry, of course, I'm not going to do that. But right now, there is still sound wave energy striking your eardrums. Okay, now I'm going to lower it. Like so, and this right here is back down to 5,000 hertz, 500 hertz, 50 hertz, and so on. Okay, there's a couple of terms associated with the frequency spectrum and also a few other quantities. They're a little bit confusing, so let me describe these terms to you. Actually, before I do, let me erase this. Have you ever listened to the sound of your own recorded voice? It kind of sounds annoying, right? It's kind of whiny and high-pitched, and you're like, oh my God, that's horrible. Well, I hate to tell you this, but that's exactly how everybody else hears you. So then therefore, when you speak with your own voice, why does your own voice sound lower-pitched than when you hear it when it's recorded? And as I said, when it's recorded, that's how everybody else hears it. When you hear your own voice, you're not just hearing frequencies that are propagating through the air. You're also hearing frequencies associated with the vibration of your own skull. So for example, do the following. Place your hands on your head kind of like this, and then go, ah, or something like that. So it just starts talking a little bit. Do you feel a vibration? Like so, you're going to feel a vibration. So then therefore, when you speak, when you hear your own voice, you're hearing, yeah, sound waves propagating through the air, but you're also hearing sound waves of literally your own skull rattling. So then therefore, those low frequency sounds that you're hearing from your own head rattling, nobody else hears that. They just hear the sound waves propagating through the air. So when you listen to your own recorded voice, that's how everybody else hears you. I hate to tell you that. Okay, now these terms that I was about to mention. Okay, first of all, what is called infrasonic. Okay, all of these words, by the way, have the word sonic in them, so it's very easy to get them all confused. Okay, infrasonic refers to frequencies, specifically frequencies that are less than 20 hertz. So it's below the low-end portion of human hearing. Seismic waves, for example, typically have infrasonic frequencies in the range of like 3 to 6 hertz or so, something like that. You're never going to hear seismic waves themselves. For that reason, their frequencies are just simply too low. But then, kind of like at the opposite end of the spectrum, there's what's called ultrasonic. Okay, ultrasonic frequencies are frequencies that are greater than 20,000 hertz. So this is above the audible range of human hearing. Dogs, for example. Dogs can hear ultrasonic frequencies up to about 40,000 hertz. They have a much better developed sense of hearing than we do. This is why dog whistles, when you blow them, if you've ever done this before, you don't hear anything. Your dog certainly does. The reason why is because dogs can hear up to the ultrasonic frequencies of around 40,000 or so. Okay, now, kind of like similar words are the words subsonic and supersonic. Okay, these do not refer to frequencies, they refer to speeds. Subsonic refers to the speed of the source of sound being less than the speed of sound. So when I walk across the room and I talk when I do, I'm a subsonic source of sound, because I'm traveling less than the speed of sound itself. That's what's called subsonic. So the speed of the source is less than the speed of sound. Okay, then you can probably guess what supersonic means. Supersonic is when the source of the sound is greater than the speed of sound. Its speed is greater than the speed of sound. What happens, for example, when a plane goes supersonic and, quote, breaks the sound barrier? We'll get to that later on in the chapter. But supersonic is another speed. It's the speed of the source is greater than the speed of sound. So all these words kind of sound similar to each other because they have the word sonic in them, but two of them refer to the frequency spectrum, the other two specifically refer to speeds. Yeah.
So what would like a firework
What would a firework be?
be? Like
That's-
how you see it?
Well, the reason why you see it before you hear it is because if you're some distance away from it, or like, for example, when you see lightning before you hear the thunder, it's because the speed of light is enormous compared to the speed of sound. So when thunder, for example, occurs, the reason why it does occur is because the lightning bolt itself heats up the air around it. The temperature of the lightning bolt, that plasma, by the way, is in the neighborhood of like 5,000 degrees or something like that. When it heats up the air, it basically creates a partial vacuum. The air basically rushes out when it's been heated. However, immediately after the temperature cools, what happens to that air? It rushes back in. And when it rushes back in, that's the thunderclap itself. So it basically more or less occurs at the same time, but of course you see the bolt before you hear the thunder because the speed of light is enormous compared to the speed of sound. Or like, for example, somebody far away from you bounces a basketball. Have you ever noticed there's kind of like a delay between seeing it and hearing it? Same reason. Okay, moving on from there. A little bit on loudness. Okay, the word loudness is a physiological term. It's just describing our senses. However, it corresponds to a specific physical quantity, one you actually haven't seen yet here in class. This is where you get introduced to it. It corresponds to the physical quantity called intensity. Intensity is just a definition, and as we'll see, there's kind of two ways to think of it. But the definition itself, first of all, is the following. Intensity is usually just abbreviated as capital I, and by definition, it's equal to power divided by area. Power divided by area. So in terms of the units here, just in metric SI units, of course, that's all you have to worry about. A power in the numerator, remember, is energy per second. Joules per second, that's measured in terms of watts. And then we're dividing it by area here, for example, in terms of meters squared. So watts per meter squared are the basic metric SI units of intensity. Okay, now as I said, there's kind of two ways to think of intensity. Here's, first of all, the first way. Okay, once again, let's say that we have right here a source of sound. Just think of it as myself with a specific frequency. I just go, like so. And then simple periodic waves propagate outwards from there, blah, blah, blah. In order for me to produce the sound, however, that requires a certain amount of energy on my part. There's a power output associated with the source, the amount of energy that I need per second to produce the sound. That is, we just refer to that as P source. Just the energy that I need per second to produce the sound is associated with the production of the sound wave. And it then propagates outwards along the spherical wavefronts, as I mentioned. So right here is a spherical wavefront like so, where the radius of this sphere, let me indicate as R. What happens to the energy as time goes on? Well, it just spreads out over the increasingly larger and larger surface area of the sphere. Remember that the geometrical formula for the surface area of the sphere is 4 pi r squared. So the intensity of that sound wave at this location R is equal to the power output of the source divided by the area over which that energy is spreading, 4 pi r squared. Notice that, like the law of universal gravitation from chapter 6, the intensity obeys an inverse square law relationship. An inverse square law relationship just comes from the fact that we live in a three-dimensional universe. The energy is spreading out over the three-dimensional surface of a sphere. So the way that an inverse square law works, if you recall, is the following. If you're twice as far away from a source, then the intensity in this case would be 1/4 of its original value. If you're 3 times further away from the source, then the intensity is 1/9 of its original value, and so on. That's how an inverse square law works. Now that's the first way to think of it, Danny. There is a second way to think of it, however. Think of it in terms of being a receiver. You listen to the sound. So right here, we'll say is an area. Think of it as the area associated with your eardrum. And so then therefore, at this location, the same intensity I can be thought of as the amount of energy that you receive per second, P receive, per the cross-sectional area of your eardrum. So how much energy per second is passing through your eardrum? In other words, per meter squared, that's the intensity of the same sound wave. So you can think of it in terms of the production, or you can think of it in terms of receiving, either way. Okay, now how does this correspond then to loudness? Well, physiologically, what we perceive as a doubling in loudness corresponds to an increase in intensity by a factor of 10. Corresponds to an increase in intensity by a factor of 10. This allows us to set up a scale, specifically a base 10 logarithm scale to describe loudness, and that's what the decibel scale is. Okay, before I get to the actual scale itself, once again, in terms of loudness, how does our physiology here work? So before I get to the actual scale, let me describe to you first of all a couple of numbers. First of all, the softest audible sound. Okay, the softest audible sound, the intensity associated with it, called I0, is exceedingly tiny. It's only a trillionth of a watt per meter squared. It's referred to as I0. A trillion is 1 times 10 to the minus 12. This is the softest audible sound that you can hear. Now, what would the softest audible sound, I0, sound like? Well, it would probably sound something like this. Well, Sean sitting right in front of me could probably hear most of the words that I was saying. I said, if you can hear me, you're probably hearing 1 times 10 to the minus 12 watts per meter squared. However, Brian on the other side of the room probably didn't hear anything at all, or very little. The reason for that is because of the inverse square law. So Sean right in front of me was roughly hearing I0, 1 times 10 to the minus 12 watts per meter squared. But Brian on the other side of the room is 3 or 4 times further away from me than he is. So then therefore, because of the inverse square law, Brian was only hearing 1/9 or 1/12 perhaps of what I was saying, or rather what Sean was hearing because of the inverse square law, 1/9 or 1/16. I guess I should say 1/4 squared is 1/16. So if Brian on the other side of the room hears something that's less than 1 times 10 to the minus 12 watts per meter squared, he's not going to hear it. He's not going to hear anything at all. And when does sound become painful? Well, this is called the threshold of pain. The threshold of pain is an intensity that's a trillion times bigger than this. It's 1 watt per meter squared. This is when sound literally becomes painful. If you subject yourself to this intensity, then you start to damage your hearing. I'll get to that a little bit later on. But if you get louder still than this, you eventually get to the point where we don't even really bother to think of it as a sound wave anymore. It's just basically this enormous pressure wave with a huge amplitude associated with it. If you go past the threshold of pain, you eventually get to a point where the amplitude of the wave is so big that it literally starts to break apart your flesh. In other words, you'll be killed. This is called the threshold of death.
Oh,
How many bands in man?
I never thought. Yeah, really.
The threshold of death is an intensity that's 1,000,000 times bigger than this. It's 1 times 10 to the 6th volts per meter squared. What exactly would be the threshold of death? Well, imagine standing next to a bomb. Bomb goes off. If the shrapnel doesn't kill you, what does? It's the pressure wave. The amplitude of the pressure wave is so big that it literally blows apart your body. We don't even really think of it as sound at that point because the amplitude is so huge. That's an intensity equal to 1,000,000 watts per meter squared. That's enough to basically blow you apart. That's called the threshold of death.
So basically what you're saying is a bomb is an inaudible with loudspeaker. So.
No, when a bomb goes off, where does that energy go? Some of it becomes the pressure wave itself. If the amplitude of that pressure wave is enough, it will give you an intensity that's bigger than this number, then it's going to blow you apart. Okay? All right, now as I said earlier, because of this fact that we perceive a doubling in loudness with an increase in intensity by a factor of 10, this then very easily allows us to set up a base 10 logarithm scale that we then use to describe loudness. This is the decibel scale. Let me describe how it works. Okay, the decibel scale is written out in the following way. Like so, where I0, the softest audible sound, appears in the denominator of the ratio in the parentheses for the base 10 logarithm, 1 times 10 to the minus 12 watts per meter squared. Okay, the sound itself has intensity I. The logarithm here by itself is usually just a decimal. It's referred to as a bell, B-E-L. And then to get rid of the decimal, we just basically multiply it by 10. When we do, we then end up with the amount of decibels. Okay, decibels is abbreviated as dB. It's important to realize, by the way, that both the bell and the decibel is just a name. There are no units, you'll notice, associated with this quantity. We have a logarithm which has this ratio, the units cancel out, you end up with nothing. So there's no units at the dimensional quantity. So then therefore, both a bell and a decibel are just a name. Sometimes, unfortunately, the amount of decibels is also referred to as the intensity level. I know that kind of sucks. There's the intensity of the sound, and then the intensity level, the amount of decibels, and that's just the way it is. The amount of decibels is sometimes referred to as the intensity level. Now, getting a handle on the decibel scale, how it works, is really easy. So let's just take a look at an example to do so. So in my example here, the first 3 parts, parts A, B, and C, will give you an idea very quickly as to how the scale works. Then once we understand how the scale works, then we'll take a look at a couple of cool numbers, D and E. So in parts A, B, and C here, you'll recognize very quickly that there's a very simple pattern. So what we're supposed to do is, given beta, the intensity level, the amount of decibels, find I. Solve for I, the intensity of the sound itself. Once again, with parts A, B, and C here, there's a really simple pattern that gets picked up. So let's take a look at, first of all, part A. All right, so we're given that the amount of decibels here is equal to 0. So just plug that in here on the left. And then what I have to solve for here, once again, is I. So to solve for I, first of all, just cancel out the 10. Just divide it out, like so. And then what's my next step here? How do you get rid of a base 10 logarithm? This is not a natural log, it's a base 10 log. So how do I get rid of a base 10 log? How do you go from logarithmic to exponential form?
10 to the power.
Yeah, 10 to the power. So it's 10 to the 0th here on the left. And then on the right-hand side, when you go 10 to the log of the stuff, what do you get? Just stuff. Now, 10 to the 0th is just 1. So this then means that the intensity of the sound is I naught, 1 times 10 to the minus 12 watts per meter squared. In other words, 0 decibels, by definition, is the softest audible sound. It wouldn't make any sense to describe 0 decibels as something that is louder than this or softer than this, because if it's softer, you wouldn't be able to hear it anyway. So the scale, in other words, is defined in terms of I naught. Okay, now watch what happens for parts B and then C. Okay, so for part B, beta is 10 decibels. So put it here on the left-hand side of the expression, like so. And then once again, just solve for I. So divide out the 10 here on both sides. When I do, I end up with a 1 here on the left-hand side. And then go from logarithmic once again to exponential form. So the left-hand side ends up being 10 to the first power. The right-hand side is just stuff. So, and then just solve for I. So the intensity here is 10 times as intense as what it was up on the top board. It's 1 times 10 to the minus 11 in this case, watts per meter squared. Now remember what I said earlier, what we perceive as a doubling in loudness, that corresponds to an increase in intensity by a factor of 10. So this sound here is 10 times as intense as it was up on the top board. This means it's twice as loud. So 10 decibels is twice as loud as 0 decibels. That's the basic way in which the pattern works. For every increase in 10 decibels, that corresponds to an increase in intensity by a factor of 10. Therefore, we perceive it as twice as loud. So then therefore, 20 decibels is twice as loud as 10 decibels. 30 decibels is twice as loud as 20 decibels, and so on. How many times louder than 0 decibels would 20 decibels be, by the way? 4 times as loud. Because 20 decibels is twice as loud as 10. 10 is twice as loud as 0. Therefore, 20 decibels is 4 times as loud as 0. That's the basic way in which the pattern works. Now, when I speak to you, if I speak to you in my normal conversational voice, which is going to kind of sound like this, I'm obviously not going to use my lecture voice when I'm talking to somebody who's standing right next to me. If you're right next to me, you're hearing probably something around 30 decibels or so, something like that. That's typical for conversational voice. But if you're on the other side of the room, because of the inverse square law, you're going to hear something that's less than that. So if you're 3 times further away from me from the inverse square law, the intensity of the sound that you're hearing is 1/9 of what Jacob, for example, is hearing. 1/9 is about 1/10. So then therefore you're hearing an intensity as 1/10 of what he is hearing. This means that it's half as loud. It's 10 decibels less. So if he's hearing 30 decibels when I speak, on the other side of the room, Natalie, for example, is maybe hearing 20 decibels. That's the basic idea. If I speak to you a little bit louder, as I do with my lecture voice, then it's probably somewhere in the neighborhood of 35, maybe 40 decibels, something like that. But that's the basic idea of how the scale works. Watch it happen here for part C. Same idea. So for part C, just check here, 20 decibels, put that then on the left-hand side of the expression. Like so, and then immediately just cancel out the 10. By the way, the Richter scale, which describes the intensity of seismic waves, works exactly the same way. It's a base 10 logarithmic scale defined in terms of a specific seismic wave. It's just with the Richter scale, however, we don't bother to multiply by the 10 like we do with the decibel scale. So for example, right here, let's say that on the Richter scale, you would have an intensity of 6. Well then therefore, if you have a value here of 6, This then means that it's 10 times as intense as a value of 5. It's 100 times as intense as a value of 4, and so on. So the Richter scale works exactly the same way. An increase in intensity by a factor of 10, that's 1 more on the Richter scale itself. That's the basic idea as to how that works. Here in the decibel scale, it's basically the same thing, it's just that we multiply it by 10 to get rid of the decimals. All right, so just do a little bit of canceling here. This is a 2. Okay, go to exponential form like so. And then just cross multiply and solve for I. Like so. So this is 100 times as intense as 0 decibels. So then therefore 20 decibels is 4 times as loud. Okay, mathematically the number here is 1 times 10 to the minus 10. But that's the simple pattern that gets picked up here. You increase in 10 decibels, you increase intensity by a factor of 10, it's twice as loud. That's the basic idea as to how it works. Okay, let's take a look at a couple of the fun numbers for D and E. Well, yeah. Hey, you can probably get the idea here. Okay, so for D, 120 decibels. First of all, let's just do the math and solve for I. I'll plug 120 here to the left-hand side. Like so. Okay, do the canceling first. So cancel here, this becomes a 12, like so. Okay, go to exponential form. So 10 to the 12, which is a trillion, equals then I over I naught. Solve for I by cross multiplying. So the intensity of the sound is a trillion, 10 to the 12, multiplied by I naught, which is a trillionth, 10 to the minus 12. So if you multiply 10 to the 12 times 10 to the minus 12, what do you get? 1 is 10 to the 0. This is 1 watt per meter squared. This is the threshold of pain. So how many of you have ever been to an indoor concert? Oh yeah, I have. If you go to an indoor concert, you stand right next to the speaker, you're at threshold pain. You're getting 120 decibels. How many of you have been to a concert and then the next day or so, your hearing kind of sounds a little muffled, hear a little bit of ringing in your ears? How many of you have heard that? Oh yeah, congratulations, you've damaged your hearing. You are suffering from what is called tinnitus. I've also heard it pronounced as tinnitus. When you suffer from tinnitus, literally what's happened is that your eardrum has been injured. Now, just like normal tissue, it will heal, of course, slowly over the course of a couple of days, and then your hearing will, of course, be restored. But if you do this enough times over the years, you're eventually going to impair your body's ability to heal itself, and then you're going to start to suffer from hearing damage. You're going to start to suffer from hearing loss. So how do you protect yourself from doing this? Well, the easiest way to do it is just, take advantage of the inverse square law. Walk backwards a little bit from the speakers. Because, for example, if you get 3 times further away from the speakers, the intensity will be 1/9 of its value if you were standing right next to them. Then therefore 1/9, which is about 1/10. This then means that the intensity has gone down by a factor of 10. So it's gone down 10 decibels. It'll be half as loud. So 110 decibels is half as loud as 120 decibels. It's below the threshold of pain, and you're not going to suffer from tinnitus so much. However, you may have noticed that this is somewhat difficult to do in an indoor concert venue. It's kind of hard to get away from the point where the sound is really loud to where it's soft enough such that you don't suffer from hearing damage. The reason for that, of course, is because the sound waves themselves are reflecting off the walls and the ceiling and so on. So it's hard enough to get far enough away from the stage such that you take advantage of the inverse square law in this manner. Now, how many of you are going to Coachella? Hey, if you do, you're going to an outdoor venue. Have you ever noticed that outdoor venues are always a lot softer than indoor venues? The reason for that is because if you move away from the stage in an outdoor venue, keep in mind that the sound wave is just propagating outwards as a sphere. It's not reflecting off of anything, so then therefore it's going to drop off in intensity very quickly and it will be very noticeable. So you generally really don't need ear protection perhaps if you're at an outdoor concert, except if you're right next to the speakers. Just move back a little bit, take advantage of the indoor square law, and you're perfectly fine. Now, for those of you that do go to concerts, and as I said, I go to concerts all the time. I went to one a week and a half ago, and I'm going to another one this Friday. How many of you don't like to use ear protection? How many of you don't like to do that? Use it. I'm speaking from experience. These guys here have been subjected to thousands of concerts in the last 30 years. These guys here have survived at least 15 individual Motorhead concerts. Motorhead, before Lemmy died, was the loudest rock band in the world. And I've seen it, because I remember one particular show in Chicago about 30 years ago, where it was so loud that the ceiling was shaking, and the ceiling was actually crumbling. There was dust coming down from the ceiling. It was that loud. You start to damage your hearing the more and more you subject your ears to these loud noises. So you definitely want to protect yourself. And I have to, because this is my second job, by the way, going to concerts in part. When you protect yourself with earplugs, you want to do it the right way, however. Don't buy the really big, waxy earplugs you just jam into your ears like that. The reason why is because, yeah, okay, it's going to protect your hearing, but you're not going to hear anything. You're not going to be able to hear all the frequencies of the music that you're there to enjoy. So frankly, why bother going if you can't hear anything? So don't get those really big, waxy earplugs and just jam them in. Instead, go to CVS or something like that, and they always sell in these little packets of about 50, these little foam earplugs. The ones that I get are kind of cone-shaped, they're yellow and pink. And then what you do is just take those earplugs and just lightly set them in your ear canal. You don't jam them in like so, you just lightly set them in your ear canal. And when you do, it's going to block enough of the sound so it lowers the intensity below the threshold of pain, yet you can still hear all the music that you're there to enjoy. You definitely want to protect your ears, especially the more and more you do this. I remember once about 10 years ago, I went to a show at a bar on Hollywood Boulevard, and I was right up against the stage, and I forgot my earplugs. And it was so loud that my ears afterwards rang for 5 days. That's not good.
With these kind of earplugs work?
Something like that. Now, how many of you use earbuds? Okay, I certainly do. How many of you really like to crank the music up really loud with your earbuds? That's a bad idea. Because if you go all the way up to the top of the volume on an iPhone or something like that with earbuds, you're getting about 120 decibels. You're at the threshold of pain. If you do this enough, you'll damage your hearing with just earbuds alone. There are people that are a little bit older than you, in their 20s and in their 30s right now, that have permanently suffered hearing loss because of this, just using earbuds. So just be careful when you do that. Do you guys know who Pete Townsend is, by the way?
Yeah.
He's a guitarist in The Who, the old rock band from the 60s. They're one of the loudest bands in the world. He was legally deaf by the time he was 25, just because he damaged his hearing so badly because of all the loud instruments. So you just want to protect yourself. It's easy to do. Okay, take a look at the last portion here of this problem. Finish up. You can probably guess where I'm going with this. Yeah, this is the threshold of death. Watch what happens at 180 decibels. So set beta equal to 180. Like so. And then just solve for I. So cancel out like so, making this an 18. Okay, go from logarithmic to exponential form. So 10 to the 18th equals the ratio. And then just solve. So the intensity of the sound here will be 10 to the 18th times I naught. Notice how the math here works. 10 to the 18th multiplied by 10 to the minus 12. So 10 to the 18th multiplied by 10 to the minus 12 is what?
10 to the 6.
10 to the 6 is a million. 1 times 10 to the 6. Watts per meter squared, that's the threshold of death. So we generally don't even bother talking about decibel levels that are greater than this, because at that point, so what? It's not really a sound wave, it's just a huge pressure wave. Give you an idea of something in between the two, 120 and 180 decibels. Have you ever seen airport workers out on the tarmac and they have those huge ear mufflers on? Those are there for a reason. If you stand next to a jet engine when it's at full throttle, it's 140 decibels. It's 4 times as loud as the threshold of pain. If somebody stood next to a jet engine without ear protection, take the earmuffs off, take them out of your eardrums. You're going to permanently suffer hearing loss. You're probably going to rupture your eardrums. They're going to pour out in torrent blood if you do that. So that's why those guys are always wearing that. But protect yourself at concerts, it's easy to do. Okay, take a look here at the agenda board. With respect to the agenda board, there's just a short web assigned due at the end of this week based in part on today's lecture and a little bit more, but it's easy enough for you to be able to figure out. It's only 3 problems. And then on Thursday, where do we meet? What time? 9:15 a.m.